So there we are recording now. So again, y'all, today, really what I wanted to do was ask you guys, were there any questions that you wanted me to go over from the review? And whatever questions you guys need, y'all, that's what we're going to do today. We're going to take today to see if we can't figure some of this stuff out. And y'all, remember one thing I had asked you guys about the other day was if you felt that there was anything that we needed to update. Let me come back this way. If there was anything you guys felt like we needed to update for the formula sheet, and I'm just going to pull that up so that I'll have access to it right here. But y'all, if y'all feel like there's anything I need to update in terms of the formula sheet, please let me know, and I'll be more than happy to add that in here so that you guys will, have like a little bit more of an updated version. Uh-huh. Uh-huh. Tangent, like both of them together? No, it's all going to be pretty straightforward stuff, y'all. And so, like, the one thing I really kind of want to emphasize here, you guys, is that, like, so look, let me scroll down just because I really want to emphasize something, and I'll come back up in a second. But let's see, these are limits. Okay, this is still chapter 4. This is still chapter 4. I don't know why it came out looking like that. That's a little weird. Okay, so yeah, I don't know why it came out looking like this. Is this how it looks like? I don't know. We'll fix it in a little bit. I don't know why it coming out real. I don't know. That looks very weird, right? Like we never saw this kind of business before, right? Um, but let me see. Let me see if I can do something here, you guys. I don't know why it came out looking like that. And if I need to, I'll just do a little copy and paste as we go through, right? But so let me do this. Here we go. Okay, so when you're talking about like the antiderivatives, right? So the antiderivatives or the integrals and stuff. Yeah, I want you to notice, y'all. Remember the problems all these problems that I picked here out of the review. These problems all came out directly from the homeworks that we've had before. So any kind of problem, any kind of antiderivative problem or integral problem you're going to see is going to come directly from here, right? So there won't be anything, like out of the ordinary. Everything that we have on this review, you guys, I pulled it directly from your homework. You know what I mean? So all the problems on here, let me ask you a question. Should we try number 36? Because that one has both trig functions, right? Okay, so look, this is what we're going to do. Let's try number 36. Let me copy and paste it. Okay. And so let me do that. Okay, I have this copied right here. Let me, like here's 36. If you look, I don't know why it came out that way, but it's okay. We'll just drop it right here. Okay, so it says evaluate the integral by making the given substitution. Okay, so it's telling me we're going to let u be equal to 4x. So, y'all, we're doing an antiderivative here using this substitution idea, right? So if you remember, wouldn't we do this? Wouldn't we find du dx? And what's the derivative of 4x? Wouldn't it just be 4, right? So that was my step number 1. This was my step number 2. My step number 3 was let's move my dx term this way, right? Yeah, so we're going to have 4 dx, right? Okay, so then what I'm going to do is I'm going to come back over here, y'all, to my problem, and I'm going to say, look, this is going to be the secant of u times the tangent of u, right? Now, I have a dx here, or 4dx. Here I just have a dx. If we did this, if we did 1/4 du, or divided both sides by 4, wouldn't we come up with that? So right here, y'all, I can put a du, but I'm going to bring my 1/4 out to the front because it's just a constant term. Okay, so now this is the part I don't want you to get too nervous about. So we're trying to find the antiderivative of, say, secant u tangent u, right? Yeah, this would be my approach. So guys, if I was sitting where you're sitting, now remember the test is going to open up this afternoon, y'all. They'll open up at 2:50. It's due by next Wednesday, right? Guys, Monday we're not going to have class. So Noel, don't sign in on Monday because you'll be there by your lonesome, right? Or I don't know if else is Matias. Are you with us online today too? Let's see, Matias, you're there too. Okay, so guys, don't sign in Monday because you'll be here by yourselves. But remember, I'm giving you that day to take the test. So this is what I would do if I were you. If you were uncertain, how do I find the antiderivative? What I would do, y'all, is I would come back over here, and I said I'm going to do it, and I'm going to drop it in here today. I just haven't done it yet. I'm going to come over here to my formula sheet, right? And I'm actually going to go to the formula sheet for test one, and I'm going to explain why I'm going to go to the formula sheet for test one. Because when I start looking at derivatives, let me see if I can find it. Here we go. So when I look at, say, this part right here, remember what this means. The derivative of secant is secant times tangent. So wouldn't the antiderivative of secant tangent just be secant? Does that make sense? Right? So that would be my approach. So if I see an antiderivative, basically think about it this way. The antiderivative of cosine is sine. The antiderivative of a negative sign is cosine. The antiderivative of secant squared is tangent. You see what I'm saying? Because if the derivatives are this, then the antiderivative goes backwards, right? It's like an inverse thing, right? They're inverse ideas, right? Derivatives and antiderivatives. So what I would say is, look, if I have a secant x tangent x, the antiderivative would just be secant x. So when I come back over here and I say, look, I see a secant u tangent u, the antiderivative would just be 1/4 secant of u. And then we need to go ahead and, yeah, resubstitute that back in. And we said that u was 4x, so we're just going to put a 4x right there. And then, yeah, that's very good. John says, look, they already did the plus c, so I don't have to worry about that part. And now I'm good. Does that make more sense? Definitely? Yeah. Okay, good, good. So yeah, the problems you're going to see, y'all, and again, remember what it is, when I made the test, y'all, what I did was this. I came back over here to my review. And what I did is when I made the test, I picked questions directly out of this thing here, right? So out of these 40 questions, all I did, I just chose 20, right? So the idea is if you know how to do these 40, all you're doing is you're just doing like a smaller set of it, right? It's like if you've already done the 40, now I'm going to say, do these 20 again. Right? Tell me, John. Well, so let's take a look. Okay, so John's question is, do we have any approximations on Riemann sums? Yes, we do. So look, we have 32 and 33. So look, let's do both of those just to make sure, again, we're good with this stuff here. And you guys watching from home, guys, if y'all have any questions, if you guys have any questions, you guys, let me know. I want to make sure that I'm answering any questions that you guys have, okay? Oh. Yeah. Okay, so
I can't just actually draw stuff immediately. My future is actually open up my download library,
okay,
screenshot it, record it, and together.
okay. Yeah, it takes a little time to do, right? Okay, so look, y'all, here's the problem. It says approximate the area under the curve, graph below from x equals 3 to x equals 6 using left point approximation with 3 subdivisions. Okay, so let's see if we can remember how to do this. We're going to go from 3 to 6, right? And we're going to make 3 subdivisions. Okay, so y'all, do you agree we're going to make 3 subdivisions? The way we did this before is we said we're going to take 6 minus 3 because we're going to take the bigger number minus the smallest number. That's going to give me 3. And then we're going to divide it by the number of subdivisions. So the number of subdivisions here is 3. So 3 divided by 3 is 1. All that's telling me, y'all, that's telling me how wide my rectangles are going to be. My rectangles are going to be with a width of 1. So look, I'm going to do it like this. The first one starts at 3. The next one starts at 4, 5, and 6. So look, here's one rectangle. And we're going to do it using what we call left endpoint approximation. That means that that point is going to be the height of my rectangle, right? Now I'm going to do the same thing right here, 2, and I'm going to do the same thing right here, 3. Does that make sense how we did that? So far, are we good? John, am I okay? Okay. So now that I have my rectangle, okay, all we're trying to do is find the area of each of those rectangles. So remember, the formula for the area of a rectangle, y'all, length times width. Okay, so look, we're going to have 3 rectangles, A1, A2, and A3. Okay, so the length or the height, what would you say the height of that first rectangle is? Yeah, I'd probably guess right about 3. Okay, the width we know is 1, right? The second rectangle, right about here. Yeah, I might go a little bit higher, maybe 3.6 or whatever. You know what I'm saying? But again, y'all, you want to take a guess. You want to take a good guess. I'd probably say about 3.6 times 1, and and then if you take a look at the last rectangle right here, y'all, yeah, that one's pretty much at 4 times 1. So then all we're going to do is just add up those numbers. So that's 3, 3.6, and 4. So that's 6.6 plus 4. Wouldn't that be about 10.6? Okay. And there's my Riemann sum. So let me ask you a question. Was that hard to do? Yeah. The graph is right there, right? Okay, so look, y'all. I agree. Riemann sum is kind of a pain in the butt, right? And this, guys, the main reason why I'm kind of going through this is because it's the introduction that when we're finding integrals, we're really finding the area underneath the curve. And it's, the nice thing about it, it's geometric, right? And I mean, we all took geometry at some point in high school, right? 10th grade, 11th grade, 9th grade. And I know people who've taken it in 8th grade. Guys, I don't know if I ever told you the story, but I failed math 5 years in a row. 7th, 8th, 9th, 10th, and 7th, 8th, 9th, and 10th grade, 4 years in a row. Sorry.
What? You didn't get to come back?
I did well enough. I would fail like a semester. You know what I mean? So like in my freshman year, I failed the second half of Algebra 1, but my grade in the first half of Algebra 1 was high enough so that I passed the year. My sophomore year, guys, I failed the first half of geometry, and I remember this. I got a 69. And I remember going to the teacher saying, "Come on, sir, I got a 69." And this is what he told me. He goes, "Isn't that such a shitty grade?" And I was like, "It is, it is." He's like, he goes, "But look, this is a good thing. We still have a semester to go. You just need a 71, and you can make it through. So if you just put in this much more effort, right, you can pass, right?" Now, had this been in May, I'm sure, I'm guessing he might have given me a point or two, right? But the fact that we were still December, he didn't want me to kind of like, okay, I don't have to do much. You know what I mean? The idea was work harder so that you don't, and I did, right? But I'll tell you this, guys, my senior year, I had to retake geometry because I took this geometry called informal geometry, so we didn't have to do all the proofs and stuff. It was kind of like a watered down, so I had to retake it my senior year. Anywho, but I know, no kidding, right? It's kind of ridiculous. Okay, so look, y'all. We're going to do the same kind of thing here, right? The way I'm going to do this problem, y'all, is I'm going to make a little number line here. I'm going to go 0, 2, 4, 6, 8, and 10, okay? And I'm going to make something that looks kind of like this, I guess. Okay, and what's my highest number? 10.4. Okay, so look, right here, you got 0, y'all, and I'm just going to kind of do it like this. That number is 10.4. At 2, I'm just a little bit lower, 9.9. At 4, we are at 9.5. And again, I'm not doing this, super accurately. I'm just plotting numbers here. 9.1, 8.7, and 10 is 8.3. Okay, now it's telling me, it says liquid leaked from a damaged tank at a rate of RT liters per hour. The rate decreased as time passed. Okay, it says in values at the rate at 2 hour time intervals are shown in the table. Okay, find the lower and upper estimates for the total amount that leaked out. Okay, so look, y'all, we're going to do this twice. We are going to make some rectangles here. This is what my first rectangle is going to look like. That one there, that one there, this one here, this one here, this one here. Okay. Now, one thing I want to emphasize, y'all, just by looking at my picture, the width of those rectangles is all what? They're all cubes. Okay. Y'all, all I'm going to do is find the area of each of those rectangles. So, question, does everybody agree for the first rectangle, I would take 10.4 times 2? The second one, 9.9 times 2. This one, 9.5 times 2. 9.1 times 2. 8.7 times 2, right? All I'm going to do now, y'all, is take those numbers and go. Okay, so look, remember what I'm doing now. I'm going to take all these, whatever answers I get here, I'm going to add them all up, right? So look, if I'm adding these numbers all the way down to 8.7 times 2, couldn't I really factor out a 2 and then I'm just adding each of those numbers together, right? Guys, it's just like a way to save yourself a little bit of time, right? But I mean, you can definitely do it the long way. So look, this is what I'm going to do. 2 times my height, 10.4 plus 9.9 plus 9.5 plus 9.1 plus, what is it, 8.7? Leave out the last one, right? 95.2. Okay, now look, y'all, that's the answer that I'm coming up with. My question to you, is that my lower estimate or is that my upper estimate? Okay, so look, if you're going to do the other one, this is what you would do. You would now have that rectangle and you would not include that one there, right? So now this is going to be the lower estimate, right? So the one we just did was the upper estimate, and we came up with what, 95.2? So if I was going to do the lower estimate, I would still take these numbers here, but instead of using the 10.4, I'm going to use the what? The 8.3. So check this out. On my calculator, all I would do is I'd go second entry, and where that 10.4 used to be, I'm going to replace it with an 8.3, right? And I'll hit enter, and look at this one, 91. Isn't that the lower estimate? Because it's obviously the smaller number, right? And now we're done. So guys, let me ask you a question. I agree. I think the first time we went through min and sum, it probably seemed like a real big pain in the butt. And I don't know, maybe that was me that day. Maybe I was off, and I wasn't explaining as well as I could. What I'm hoping is that today, this part seems easier to do. So that the one that we just did right now? Like the one we just did? Like this one? Uh-huh. Yeah. And again, remember what we're doing here? These things, y'all, these are approximations, right? Because that's exactly what we're doing, right? So again, we're finding approximations here. But what I'm hoping is that now that we've gone through these two problems, and it looks like those are the only problems that are like Riemann sum type problems, I'm hoping that, if you see one of them, or maybe you see both of them, hopefully there's only one, right? But if you see both of them or one of them, you're going to say, okay, look, you know what? I know how to do this now. I feel better about it. All right, let's see. Y'all, any other questions that anybody wants to ask me at all? And guys, those of you at home, Noel and Matthias, if y'all have any questions, let me know too, guys. I don't want y'all to feel like you're left out because you're not. I'm sorry. So I don't want to go through like every single one, right? That's the idea of the review is you're supposed to come in and, ask me which are the ones that you struggled with, right? Because otherwise we sit here and just, on the resume. Okay, tell me. Okay, yeah, the volume one. Okay, so look, let's take a look at this one here, and let's see if we can't figure it out. You know what? I probably have it on this deal right here. What number was it anyway? Number 18. Okay, so look, let's do this. Let's come back to number 18. Here we go. Okay, so let's see if we can't figure this thing out. It says a box with no top is made from a rectangle of dimensions A being 15 inches and B being 12 inches by cutting a square of side X at each corner, turning up the sides. See the figures. Determine the value of X that results in a box with a maximum value. Okay, so look, y'all, I'm going to zoom in a little bit here. And what all they're telling me is the distance from here to here is that's the 15, because that's the A. I know they wrote it really small. And the distance from here to here is the 12, right? Okay, so what we're trying to do here, y'all, is we are going to fold our box along this line. We're going to fold our box around that line. We're going to fold our box about that line and that line as well, so that we're going to end up with a box that's going to look an open top box that looks something like this. So there we go. Okay, there's our box. Okay, so look, y'all. If I didn't draw it, well, I'll put it this way. If this was the 15 that went from here to here, then wouldn't this piece here be something like a 15 minus 2x? Right? Because we cut off a little bit of x right there, and we cut off a little bit of x right there, so that that distance in the middle would be 15 minus 2x. Does that make sense? And let's see. If this whole thing here used to be 12, and we cut off a little bit x there and a little bit of x there, wouldn't that side there be a 12 minus 2x? Right? So look, here's my 12 minus 2x. And then isn't the height of my box x? Right? Because remember, isn't x the distance from here to here? So when we fold up those sides, that's going to be my height, right? Okay, so now let's take a look if we can figure out. So all I'm doing so far, y'all, I haven't even looked at step number 1. All I did was draw my picture, just so I get an idea of what the box is going to look like. Okay. So now, number 1 says express the volume V as a function of x. So y'all, if you remember, the formula for the volume of a box is length times width times height. So we're going to say 12 minus 2x times 15 minus 2x times x. Okay. All right. Now it says determine the domain of the function of v. Okay. So what we mean by the domain is we're trying to figure out how big of a square can we cut out, right? How big can x really be? Well, I need this side. I need both of these sides here, y'all, to be positive values, right? So what I'm going to do is I'm going to say, look, I'm going to come back over here. I know x is going to have to be positive because I got to cut some of it off, right? And I know that 15 minus 2x also has to be positive. And I know that 12 minus 2x also has to be positive. Okay. Okay, so let's see if we can solve these inequalities. So first thing here, y'all, if I move the 15 that way, that's going to give me a negative 2x is bigger than a negative 15. And I would divide both sides by negative 2. Let's see, negative 15 divided by negative 2 is 7.5, right? Guys, I don't know if you remember this or not, but in dealing with inequalities, anytime you divide by a number that's negative, the direction of my inequality has to reverse. Okay, so look, we're going to do this one more time. We're going to do it right here. I'm going to move that 2 over, or that 12 over, I'm sorry. So I have a negative 2x has to be bigger than negative 12. So when I divide both sides by negative 2, I'm going to come up with x is smaller than 6. Okay? So what I want you to think about here for a minute, y'all, when they're talking about the domain, okay, look, here's the number 0, here's the number 6, Here's the number 7.5. Okay, so when they're saying x is bigger than 0, that means we're going to look at this and everything to the right of that. Okay, that's what x is bigger than 0 means. All right, when we're going to look at, say, x is smaller than 7.5, what I'm going to do is I'm going to put a circle right here, and I'm going to look at everything to the left of that, all the way down. Okay, and then I'm going to do this one last time, y'all. And when x is smaller than 6, I'm going to put a circle right here, and I'm going to do everything smaller than 6. Okay. Now I know this is really messy. It's supposed to be messy. What we're looking for is, where do we have our overlap? Where did everything overlap? Between what two numbers? Between 0 and 6. That's what the overlap is. That's going to be my domain zone. Okay, so look, yeah, it's messy, right? But the nice thing about this is all you're doing now, looking for your overlap. Okay, so we're looking for everything between 0 and 6. It says use interval notation. Interval notation, y'all, looks like that, from 0 to 6. The reason I'm using parentheses and not brackets is if I include those numbers, if I include 0, I don't have a box anymore. If I include 0, I don't have a box anymore because I didn't actually, cut anything off. And the same thing with 6. If I include 6, I don't have a box anymore. Okay, so now look at step number 3. Step number 3 says find the derivative of the function. Okay, y'all, so before I do that, right here was our original function. We had it in factored form. Let's go ahead and multiply this whole thing out. Okay, so we're going to go really slow here. We're going to FOIL this thing out. So 12 times 15, I don't know, 12 times 15 is 180. So I'm coming up with a 180. 12 minus 2x is a negative 24x. A negative 2x times 15 is a minus 30x. A negative 2x times another negative 2x is a positive 4x squared. And I still have that x on the outside. Okay. So let's see. This is giving me a 180. Minus 24 and 30 is a minus 54 with an x plus 4x squared. Okay. And I still have this x on the outside. So now my volume is going to be a 180x minus a 54x squared plus 4x to the third. Am I okay when we got to that step? Okay, so look, y'all. Now what we want to do, we want to find the derivative of v. We're looking for v prime. Okay, so we're going to find the derivative. First question, anybody know what's the derivative of 180x? 180, good. What about the derivative of a negative 54x squared? Negative 108x, okay? And then finally, what about the derivative of a positive 4x to the third? There you go. Okay. There's my derivative. So far we good? Okay. Now, step number 4 says, let's find the critical points in this domain. So y'all, the way we're going to find our critical points is we're going to take that derivative that we just came up with and we're going to set it equal to 0. Okay, now I'm not certain if it will, but I'm going to double check. And I hope it does. I want to see if I can divide everything here by 12. Let's see, 108, can I divide it by 12? Think so? Yes, that's 9. 180, can we divide it by 12? Yes, that's 15. Okay, so look, to make things easier, y'all, we can divide everything here by 12 all the way across. So that becomes an x squared, a minus 9x, a positive 15 equals 0. Okay, and let's see. Let me make sure I did that right. Yeah, we did. Okay, so you know what, y'all? I don't know if we can factor this guy. The only reason I say I don't know if we can factor this guy is because we've been looking for two numbers that multiply to what? 15, and they're supposed to add up to a negative 9. And the only numbers that I multiply to 15 are 1 and 15, that adds up to 16, and 3 and 5, that adds up to 8. Okay, so you know what we got to do here? Quadratic formula, right? Okay, so look, that's a, let's put it here. There you go. Okay, and I think I told you the other day I was trying to see if I could figure out how to solve this thing like on my calculator, and I can't. I mean, I'm sure there's a way to do it. I couldn't figure it out off the top of my head. Let me use a different color. That's too hard to see. I don't know if anybody else has found a way to solve something like that. Okay, so anyway, let's go ahead and do it to it. Okay, negative b. Negative b, if b is negative 9, b is going to be, or negative b should be positive 9. B squared, negative 9 squared, minus 4 times a times c, all over 2 times a. So let's see, this is going to give me 9 plus the square root of negative 9. When I square it, y'all, should give me an 81. Anybody know what 4 times 1 times 15? Negative 60, right over 2. Okay. All right. So now at this step, y'all, we're almost done. We're going to have 9 plus or minus 81 minus 60 is 21 all over 2. Okay. So this step, y'all, is just going to be calculator work. So this is how I'm going to do my problem. I'm going to say, I'm doing this in parentheses, y'all. Look, 9 plus the square root of 21. Now my calculator opens up parentheses, so I got to close them off again, close that off again, divide it by 2. And so I'm coming up with 6.79 is one of my answers. Okay, now my other answer, I'm going to do exactly the same thing, but instead of adding, we're going to subtract, right? Because that's what plus and minus means. It means one of them you plus, one of them you minus. Okay. And the other answer I'm coming up is, I'm going to go to 2 decimal places here, y'all. 2.21. Okay. Okay, so the 2 critical values that I came up with is 6.79 and 2.21. I'm going to write both those numbers down. 6.79, 2.21. Okay. Now, what we want to do is we want to plug in those numbers into the original volume function. Okay. All right. So let's see. If I were going to do that part, y'all, this is what I would do. I would come back here and clear this out. Let me go to my y equals. I'm going to type in my function. Y is 180x minus 54 with an x squared plus 4x to the third. Okay. So there's my function, right? I just entered in the original one that we had. Let me quit that. Let me go to my y bar. We're going to evaluate this function, y'all, at 2 numbers. One of them is at 6.79. One of them is at 2.21. Y'all, look what the first part says. The left endpoint. Which one of these 2 would be the left endpoint? The 2.21, right? Okay, so look, we're going to go like this. 2.21. And the answer that I'm coming up with here is 177.23. 177.23. Okay. And then we'll do this process again, but now we're going to evaluate it at 6.79, right? Okay, and look at the number we come up with here, negative 15.23. Okay, so which is the maximum volume? That one right there, that's the biggest number, right? Maximum volume is just saying which is the bigger number. So the bigger number is 177.23. And then part 8 says, answer the original question, the value of x that maximizes that volume. So what number did we come up with x that worked? The 2.21, right? Wasn't that the maximum? Wasn't that the x that gave us that maximum volume? So right here, y'all, I'm just going to put a 2.21. And we got it. Oh, it's right there. Into the original v, into this one right here, because it says let's find the value of v at the right endpoint and at the left endpoint. Yeah. Y'all, I want to mention something here. Remember when we did our domain? If I come back and scroll over here, wasn't the domain of my function from what, 0 to 6? So that means any number that's outside of there is not going to work. And look at one of the numbers that we came up with. Isn't that number outside of my domain? And that's why when we plugged it in, we came up with something like that. Like, how can you have a volume of negative 15? Yeah, it doesn't work, right? It doesn't make sense. So the maximum volume was the 177.23, and we got that by plugging in 2.21. And 2.21, y'all, is the number between 0 and 6, right? Does that seem better for that problem now? Like on how to approach it? So, yo, one thing I want to emphasize is, notice, before I even did the problem, the first thing I did was I looked at my picture and I said, okay, what would my box look like? The reason I want to know what the picture looks like is the picture helps me visualize what's going on. And then I can say, look, you know what? What's my domain now? And then when I say my domain, meaning what kind of numbers can we plug in? And what I know is that since we have a box here, all of those sides, y'all, have to be positive numbers. And that's why we set each one of them greater than 0, because they all have to be positive. And I know it is messy, but when you do it this way and you draw your number line, the nice thing about doing this on the number line is all you're looking for is where do we have all the overlap? The overlap is going to be my domain, right? And think about like the domain, y'all. So like right now in class, there's 3 of us. Jennifer's here, John's here, I'm here. And I said, look, we're gonna get pizza, right? And okay, what do you like? And Jennifer says, oh, I like pepperoni and mushrooms. And John says, I don't like mushrooms, right? And I say, well, I do, right? We have to get something that we all like. You know what I mean? We're looking for that overlap. Something that all 3 of us agree on is going to be the kind of pizza that we get, right? So, you know, so if it's cheese, if it ends up being cheese pizza, yeah, right? So, yeah, so it would be something like that, right? And that's kind of what the domain says here, right? There's these 3 different people. And one of them says, hey, it needs to be positive. Another one says, hey, it needs to be smaller than 7.5. Another one says, hey, it needs to be smaller than 6. Okay, what's something that's going to work for all of them? Oh, anything between 0 and 6, right? Does that make sense to y'all about the domain? That kind of example kind of makes more sense for it? Good. So Jennifer, I know you said this was one of them. Is there another one you want me to go to? Any questions, you guys? I mean, I don't want you to feel like you can't ask me, because you can definitely ask me any questions you guys have. Like, tell me what, like, but which one are you referring to? I just, when you say the rest, like, I want to make sure that I know what you're referring to here. Okay, do you remember which one it was? Okay. Yes. Okay, so I'm looking here, and like I said, y'all, I mean, that question you're going to be asking me, Jennifer, it may not even be on the test itself, because I'm looking here for ease. Yeah. And so this here is L'Hopital's rule, and I want to say that L'Hopital's rule was 4.8. You know what I mean? And so this is all L'Hopital's rule, and then this is just like, you know, finding antiderivatives, and I don't see any e's in here. You know what I mean? So that question you're asking about, I know this is 5.1. This is probably 5.2, or this is actually 5.5, because it's the use substitution business. So I may not even have put, one of those problems on there.
Sir, try number 15.
Guys, those who are watching at home, let's see, I heard something here. There's something in the chat here. 14, definitely Matias. So Matias, y'all wants us to do number 14. So let's do 14. Let me scroll back up here. Here we go. Okay. So y'all, let's take a look at 14. I'm actually going to do it from here because it should. Oh no, that came out pretty much. Let me do it over here, y'all. What are we? Here we go. Let's do a little copy and paste again. Okay. So let's copy this here. And let's paste it over here. Okay, so look what it's telling us to do here. It's telling us to evaluate the limit. Okay, so we're taking the limits as x gets bigger and bigger and bigger and bigger. Okay, so y'all, when we're talking about these infinite limits, the idea here, y'all, is we're looking at the degree of the top and we're looking at the degree of the bottom. Okay, what I mean by the degree is what is the highest power of x? So does anybody know what is the degree of the bottom part? What is the highest power of x that you see on the bottom? 2, right? That's the highest power of x. Okay, let's talk about the degree of the top part of our function. What's the highest power of x that we have here? 1. Okay, so y'all, anytime the degree of the top is smaller than the degree of the bottom, the limit as x approaches infinity is going to be equal to 0. Okay. Now I want to. So this when we covered this section, I want to say this is like 4. I want to say this is maybe like 4.7, something like that. I don't remember off the top of my head right now. 4.7, 4.6. It was one of those two sections. The way that we kind of justified this here was what we would do with our problem, and I'm just going to write it down again, y'all. I'm looking at the limit as x approaches infinity of 5x plus 4, 9x squared minus 10x plus 3. Okay, so the way we did this back when we covered this topic is we said, look, out of the denominator here, y'all, I want to factor out an x squared. Okay? And you say, like, really? You're factoring out an x squared? Yeah. And what's going to happen is that that's going to become a 9. That's going to become a 10 over x. And that's going to become a 3 over x squared. Okay? Because if I multiply x squared times each of these terms here, I would end up with exactly that part as well. Now, if I factor out an x squared out of the top, I'm like, really, an x squared on the top? Yeah, whatever I factor out here, I want to do the same thing here. Now, I'm going to end up with a 5 over x plus a 4 over x squared, so that now, y'all, I can drop those x squared. And what we have is 5 over x plus 4 over x squared all over 9 minus 10 over x plus 3 over x squared. And I want you to think about what happens as x gets really, really, really big. As x gets really, really, really large, if x is getting big here, 5 divided by a bigger number gets closer and closer to 0, doesn't it? And if x gets really big and then I square it, that means it gets even bigger, and 4 divided by a massive number gets really, really close to 0. And the same thing is going to happen with those two pieces. Both those numbers are going to approach 0. So I end up with 0 divided by 9, which is the same thing as 0. And that's what ends up happening. And that's kind of how we justify when we're taking this limit as x approaches to infinity, because we're using like a numerical algebraic approach. We're saying, okay, when you think about what's going to happen, if your denominator stays constant, but if your numerator stays constant, but your denominator gets really, really, really big, right? Then the whole number approaches 0. So guys, if I were to think about, normally there's like, say, 7 of us in here. And so if I had, like right now there's 3 of us. If I had one candy bar, and I said, I'm going to share it with everybody in the class, since there's only 3 of us, we're each going to get 1/3, right? But if everybody was here, suppose our class had 30 people, and I have one candy bar, and then we're going to share it amongst everybody, everybody's going to get a very, very small piece, right? So what happens? The piece that you get gets smaller and smaller and smaller the more people that we have, right? So as my denominator gets really big, the piece of candy that you're all able to get gets really, really close to 0, right? And that's kind of what's happening here. Anything that is divided by 0, it's going to be undefined, or it's going to approach either infinity, or it's going to approach negative infinity. Well, hold on. We'll get to that part in a minute, right? But guys, the easiest way to figure out these problems is you're going to be looking at the degrees. What I mean by the degrees, you're looking at the power of the x's on the top, the power of the x's on the bottom. And I know that when we went through this, and I'm going to see if I can find it somewhere here in my notes. Let me come back this way, y'all. And it's going to take me a little bit of time because it's somewhere here. And as you guys know, I don't label my stuff. And so it's always a big mess. I think that was what we used to text in. That's not it. This one should be it. This should be it. Here, let me see. Actually, I think this might be it. Let me see. No, let's go back. Let's chapter 3. I'm trying to see if I have it somewhere here, y'all, because I know we talked about it. It's here. Give me a second, but I know we wrote it down. Mean value thing. After that, keep down a little bit, maybe. That's max and min, so it's after that. It's got to be like 4.7. 4.6, here we go. Okay, so this is what we are looking at. Steady. In English, I tell you, you find it right here. Okay, so this is what we're going to look at, y'all. The degree of the top and the degree of the bottom. Again, we did this back in 4.6. When the degrees are the same, my limit is going to be equal to the fraction of the leading coefficient. Okay. When the degree of the top is smaller than the degree of the bottom, which is what we just had right now, that limit's going to go to 0. Oh man, what happened? Sorry. Just shot up all over the place. Okay. Too high. A little bit higher. Should be right about here. So I can find it. Okay, hit it again. I don't know, I lost it again. Anywho, but then, y'all, when the degree of the bottom is smaller than the degree of the top, then it's going to go either towards infinity or towards negative infinity. I lost it again. I don't know why. Sometimes this thing acts up a little bit. I think that file was just too big. But anywho, see, I can't even get to this deal right now. Let me close up my OneNote and see if I open it again. It will work for me. But, Matthias, did that make sense for number 14 and the approach and how we went about it? Are we good on 14 there, Matthias?
Yeah, we're good, sir.
First question is 15. I'm not sure what you're referring to. Matthias, are we good?
Yeah, we're good, sir.
That's one document all messed up. Okay, anywho, come back to where we was. Let me get back to my review. Let's see. Let's do this here. Okay, we're good. Good. Glad I got you there. Okay. Yes, here we go. That's what you're referring to. So take a look here, y'all. When I'm going to do the limit on this one, yeah, so let's do this one here. Let me see if I can get this problem here. And I'll tell you what, I'll prove 15 and 16, okay? I'll get both of these here. So let me copy this here for us. And let's see. Yeah, this is where he was. Yes. Okay. I'll find some room to work here. Okay. All right, so let's take a look, y'all. I'm going to do the same approach here. So I want you to notice in the top problem, I can factor out an x squared, and I'm left with a 6 minus 3 over x plus 8 over x squared. Out of the bottom, y'all, if I factor out also an x squared, I end up with a 10 over x plus a 9 over x squared. I'm doing that, y'all, because I need to factor out the same terms. So those are going to cancel out. So now we are taking the limit as x goes to infinity of 6 minus 3 over x plus 8 over x squared over 10 over x plus 9 over x squared. Okay, so remember what we said? We said that as x gets really, really, really big, this piece here is going towards 0. This piece here is going towards 0. So that's 6 on the top. This piece here is going towards 0. So is this one here. So that bottom number is getting closer and closer to 0, right? Now, y'all, since my denominator is getting smaller and smaller and smaller, I want you to think about what that means, okay? So look, let's do it like this. Let's divide 6 divided by, say, 0.1. 6 divided by 0.1, 60. 6 divided by 0.01, 600. 6 divided by 0.001, 6,000. So do you see what's happening as my denominator gets smaller and smaller and smaller? What's happening to my overall number? It's getting what? It's getting bigger, right? So this thing here is going to be approaching infinity. Does that make sense? Because as my denominator keeps getting smaller and smaller and smaller, this whole thing here keeps getting larger and larger and larger, right? Does that make sense? Jennifer, am I doing okay? Yeah? Okay. Now, y'all, let's take a look at 16. So first question, what do you think we can factor out of all of them? X cubed, right? We always want to take the biggest term out. Okay. X cubed, so 7, but a 3. So a 3 over x cubed, a 5 over x squared, and a minus 7. Those now are going to go away. Okay, so again, we're still taking the limit as x approaches infinity of 6 minus 8 over x minus 8 over x squared, 3 over x to the third, 5 over x squared minus 7. Okay, so remember what we said. As x gets bigger and bigger and bigger, anything divided by any kind of an x is going to be approaching 0. So on the top, we're going to end up with what number? 6. On the bottom, we're going to end up with what number? And there's going to be my limit. Right? So, good questions. I think these are important questions to know. But that's exactly what ends up happening, y'all. So when I wrote out like those rules, that I don't want to try to get back to that one page anymore because it's all, that one file is kind of it bogs down my OneNote. To me, it's like, is it important? I mean, that's kind of like the shortcut base version of it. But what I like about doing this approach here is just say, factor out the biggest power of the x, and then see what happens. And what I like about that is it's more of a like discovery type of approach, in that Okay, now I understand why the rule works the way it does. Like now I understand that when I have the power on the top and the same power on the bottom, now I understand why it goes to that fraction of the leading coefficients, because I can just see, we just did it right now, what actually happens. That's what I like about this approach. Kind of memorizing the little rules. Hey, they're going to work every single time, right? Those little formulas, those little tricks always work. What I like about this approach is it explains the why behind it, right? And I figure, guys, in Calculus 1, we're probably interested in the why, right? Like if we were taking a class that you really weren't all that interested in, I could see, hey, just tell me why, tell me how it works or how to do it. But I figure at the Calculus 1 level, we're all here because we have a genuine interest in, why does this stuff work the way it does, right? Let's see. Good questions, good questions. Y'all, any other questions you want me to answer about anything at all? 25, let's do it to it. Okay, so let's do number 25. We're going to do a definite integral here. And so let's go ahead and find the antiderivative of this problem here. Do that. Drop this down right here. Okay, so first thing we're going to do, y'all, we're looking for the antiderivative of x to the 1/3. So remember, the power rule says we're going to add 1 to our exponent. So I have 1/3. I'm going to add another 1. So wouldn't that be 1/3 plus 3/3? Right? Because I can think of 1 as 3/3. And isn't that going to be 4/3? So look what we're going to have. X to the power of 4/3. Now, we have to divide by that same power. But if you remember, dividing by fractions is the same thing as multiplying by the reciprocal, right? Now, again, y'all, we're going to evaluate this from 12 to 1. So the way I would do this, y'all, at this step, I would, and I'm going to check something real quick here, y'all. Let me try something. Back over here. And it's probably going to give me a new problem, which kind of stinks. But this was number, which one again? 25, right? Okay. Resume. Okay, let me see if I can get a 25 real quick. 25. Okay, same problem here. All right, so let me go ahead and see if we can plug in our answer and see if this thing checks out. So, y'all, I would do it like this. If I was sitting where you're sitting, I would type this part into my calculator. So let me get my calculator going right here. I'm going to turn it on, clear it out. I'll go to my y equals. Let me clear that. I'm going to have 3/4. You want to put 0.75? That's fine with me. X to the power. Now, y'all, since my power is a fraction, I'm going to put that in parentheses too. 4/3. Okay. All right, enter that. Okay, now let me go ahead and quit it. Go to my y bars. Go to my function. And we're going to evaluate this at 12. And then we're going to evaluate this again at 1. So that's what I'm coming up with right there. And I don't think it's going to allow me to do a fraction thing here. I don't think it'll work out. Yeah. So I'm coming up with 19.85485. So I'm going to check something here, y'all. 19.85. 19.85. Just curious if it lets me do that. There we go. 2 decimals seems to be good enough for my open math, right? So there we go. We got it. Guys, let me ask you a question. Was the hardest part doing this part here, the exponent part? Yeah, I agree. It's not, if it would have been like x squared, hey, we know x to the 3rd over 3. When it's a fraction, y'all, you're just, you're going to add 1 to it. So think about 1 as whatever your denominator is, 3 over 3. Or if you had a 1/5, think about your denominator, think about adding that 1 as 5 over 5. You know what I mean? And then you got it. Good question, good question. I'm sorry. What's your, is it the same question?
Yeah, it's the same question. When I run it, the fact that they actually gave it to me, like, basically the actual whole number, which I'll just multiply with each other, crazy that you can actually get what
Yeah. Let's see. Matias, Noel, do you all have any other questions you want to ask me about anything? I just want to make sure that you guys don't feel left out. Any other questions? Anybody here? Yes. Number two? Yeah, let's go back to number two. Okay, so look, number two here says a ship in nautical miles. Okay, let's do this one here, y'all. So I'm going to copy this problem because this is going to be one where I have to do a little bit of work. Let's see. Here we go. Okay, and let me copy this guy. Go back down here, and let's paste it. Okay. So it says at noon, ship A is 50 nautical miles west or due west of ship B. Ship A is sailing west at 21 knots, and ship B is sailing north at 19 knots. How fast in knots is the distance between the ships changing at 3 p.m.? Okay, so we're going to draw a picture here. So here and here. Okay. So we have ship A, so this is ship A, and we are at 50 miles. Okay, and then here's ship B, and we have something that's going to look like this, right? Because this ship here, so look, y'all, I'm going to call that X, I'm going to call this Y, I don't know, I'll call that R or whatever, Z, whatever you want to call it. Okay, so look what we have. We have this X value already, and we know that right now we're 50 miles due west. Let's see, ship A is sailing west at 21 knots. So isn't it going this direction though? Right? So look, y'all, isn't my dx dt the speed of ship A, which is 21? You see what I'm saying? Because the rate at which this is changing is 21 miles an hour. Okay. Now look what we have about our dy dt, right? Ship B is going which direction? North, right? And isn't that going to be equal to 19? Okay. So let's see. You want to know how fast in knots is the distance between ships, the ships changing at 3 p.m. So yeah, that's going to be 3 hours. So look, y'all, let me ask you a question. At 3 hours, I want to know what this distance is going to be. Wouldn't we just take 19 times 3? Because it's going at a rate of 19 miles an hour or 19 knots or whatever. Okay, so 19 times 3, isn't that like 57? Okay. This guy, we're going to take the same thing. We're going to take it times 3, right? So if we take it times 3, isn't that going to be 63? But how far were we already? 50. So don't we need to add those two numbers together? Right? Because we were already 50 miles west, right? And now we've got another 63. So isn't this total distance here, y'all, really going to be, what is it, 113? Does that make sense? I'm sorry? Is it 113? Okay. 113? Okay, so look, y'all, we're going to set up a couple of things here. If I wanted to find the value of R, okay, right? Pythagorean theorem, y'all. So wouldn't we say, isn't the Pythagorean theorem like R squared equals X squared plus Y squared? So R squared is X, which is 113 squared, plus Y, which we said was 57 squared. Okay. So look, y'all, I'm going to grab my calculator real quick so we can figure out what those numbers are going to be. So 113 squared, plus 57 squared. I'm coming up with 16,018. Excuse me. Okay, now that's R squared. So to find R, don't I need to take the square root of that number? Okay. Is it a nice 3 square root? No? Probably not, right? Usually, it rarely is. Okay, so that's what we're coming up with at this point. Okay, we'll get to that step in a second. So y'all, now what we're gonna do, because this is one of those related rate problems, right? So we're gonna use the idea here of the Pythagorean theorem. Okay. R squared equals X squared plus Y squared. Okay, So y'all, we're using the chain rule with respect to time because these distances are changing over a period of time, right? So look what we have. We're going to have 2r dr dt, right? We're taking the derivative now. 2x dx dt plus 2y dy dt. What we're trying to do is we're trying to solve for the dr dt. We're trying to figure out at what rate is that distance right there changing, okay? So that's exactly, well, we're going to do that right now. So look, first thing I'm going to do, y'all, I'm getting rid of the 2's because we can divide everything by 2, right? And if we want to solve for dr dt, all we need to do is divide everything by r. So those are going to go away. Okay? And now we're just going to do a little plug and chug. So look, dr dt equals x. We already knew the distance x. Wasn't my distance x what number? 113. So right here, y'all, I'm going to have a 113 times the dx dt was the rate at which it was changing, which was 21. Okay. Plus my y value. My y value happened to be 57 times the dy dt, which in this case was 19. And all of that is being divided by the square root of that r, which was the, okay. And this step, y'all, is just plug it in on your calculator, right? So let's do that part. So 113 times 21 plus 57 times 19. Okay. And then I'm going to divide that by the square root of 16. Yeah. And I'm coming up with about 27.31 if I go to 2 decimal places. Yeah. There we go. There's our answer, guys. Yeah. Does that make some more sense, Jennifer, on how to do number 2? Yeah? Yeah, of course, of course. So let me see here. There we go. That was number 2. Same numbers? Yeah, same numbers, right? Yeah, so what did we come up with? 27 point something? 27.31. Submit it. There we go. We got it. Well, so what it is that everybody gets different numbers, right? These problems, they're all like randomly generated, but it's like when your number, what numbers did you have? Like, you remember on your 21, or your number 2? 40 nautical miles, and then what's the rate at, instead of 21 knots, what is it? 22? Okay, so they're both 22? Okay, so it's 7 hours, right? So all these problems in all these kind of homework systems, so like whether, I don't know if you had any other math classes at SDC before this, but if you use like my math lab or like last semester in pre-calculus, John and I, we used Alex, everybody gets the same questions, but there are parameters that change. So like those parts change, you know what I mean? But the idea is like, so now that I did mine with my numbers, you can just kind of follow along and say, okay, let me plug in the numbers that I had. So you put 40 here, you'd have 22 and 22, and you'd have 7 p.m. So then instead of, you would already have the 40s and then 22 times 7, you know what I mean, to give you that full distance. But the approach would still be the same. You're just changing the numbers, right? Yeah. So, and that's the thing also, like when you take your test, like your question number 3 is going to be the same question number 3 as anybody else has, but you're probably going to have different numbers. Like, what's the likelihood that everybody's going to get the same one? Probably very low. I mean, it's possible that 2 of you guys might get the same exact numbers, but again, they're randomly generated. Yeah. Good questions. Good questions. Let's see. Any other questions you all want me to go through about anything? Don't hesitate to ask, you guys. You know I'm happy to help you guys. Let's see. What about those of you at home? Okay, we're good. Okay. Noel, do you got any questions? Or Matthias, do you got any questions? John, Jennifer, any other questions you want me to do? I'll give you a hint for like 19 through 21. What are you going to use?
2, 7, 8.
So remember, so what happens if you plug in 0? So the tangent of 0 is 0. 3 times 0 is 0. So when I can't do this, y'all remember the French guy? What was the French guy's name? Do you remember? L'Hôpital? L'Hôpital's rule, right? L'Hôpital's rule says take the derivative of the top, take the derivative of the bottom, and then plug your number in and see if that works. You know what I mean? So if you take, what's the derivative of tangent? Anybody remember? Secant squared, right? The derivative of tangent is secant squared. Okay, the derivative of 3x is just 3. Okay, so look, now we're going to have a secant squared over 3. Well, when I plug in 0, and if you want to make sure, you can do it like this. So how would you do secant and 0? So on my calculator, you can see I don't have a secant button, right? But I know that secant is 1 divided by cosine, right? So 1 divided by the cosine of 0, it's 1. Squared, still going to get 1. Okay? 1 divided by, if I took the derivative of 3x, wouldn't it just be a 3? So 1 divided by 3 is just 1/3, right? So look, this is my number 19. So look, if I were to come over here, and I were to come to my number 19, same problem. I'm going to do my little fraction button right here. 1/3. Submit it. Boom. Right. So L'Hôpital's rule. Any other questions about anything, you guys? Anything you want to ask me at all? That'd be fine. All right, so the test is going to open up today at 2:50, right? So it'll open up in about an hour's time. Again, it's not due until 12:30 on Wednesday, which is a week from today, which is the 27th. So guys, remember, Monday we don't have class. That's me giving you the day to take the test, right? So on Monday, don't show up, right? You'll be here by yourself. But if your schedule is so busy that, like I don't have time outside of our regular schedule to take the test, take it on Monday. You can take it during the same time we have class. That's me giving you the day to take it. Guys, remember, there is no time limit for the test. You can do it in chunks, right? Guys, it is due by the time we come back to class next Wednesday. So it is due by 12:30 on Wednesday, so it's not due at the end of the day. It's due when class starts, right? So don't wait till Wednesday. Obviously, I would not wait till Wednesday to do it on you. That would be the last thing I would do. But take your time. You got a lot of time to get it done. Guys, I am gonna do this over here. So let me come back this way over here. Let me get rid of that. And let me do this because I told you guys that I would put it in here. Here we go. Okay. And let me edit this here. Edit. And do this. Get my OneDrive. I don't know if you guys, but I really did Google stuff. Makes it so much easier to do. Here we go. So I'm going to shoot the test 2. Get this here. Show it. Copy the link. Okay. So again, guys, formula sheet for test 2 is right there. I will drop the notes for chapter 5 so that all one document as well. I'll drop that after a bit too. But that's pretty much it for us today, guys. Let me go ahead and stop recording.